Advanced time series forecasting goes beyond simple trend lines to capture real-world complexities like seasonality, changing volatility, and sudden shifts. In this section, we'll dive into methods such as ARIMA and SARIMA that model patterns in historical data, as well as Facebook's profit for handling holidays and irregular events. You'll also learn how deep learning models like LSTMs can pick up nonlinear relationships and long-range dependencies in market prices. We'll cover best practices for choosing the right model, tuning parameters, and validating forecasts so you can trust your predictions. By combining statistical approaches with modern machine learning, you'll be able to build robust forecasting pipelines that deliver more accurate insights for financial decision-making. ARIMA is a classical statistical method designed to forecast a single time series by combining three ideas. It regresses future values on past observations, the AR part, differences the data to remove trends and make it stationary, the I part, and models the remaining errors as a moving average of past shocks, the MA part. On the right, you see a Python workflow that brings this to life. First, it pulls historical closing prices for a stock from a data source and cleans out any missing entries. Then it creates an ARIMA model, where you specify how many past lags to include, how many times to difference the series, and how many error terms to average. After fitting that model to your historical data, it generates predictions for the next 10 periods and prints out the estimated values. This end-to-end example shows how just a few steps, data download, cleaning, model definition, fitting, and forecasting, can yield concrete numerical forecasts for financial time series. SARIMA extends the classic ARIMA framework by adding a set of seasonal terms, letting us capture patterns that repeat at regular intervals, like monthly or quarterly effects in financial time series. In a SARIMA model, you still have the non-seasonal parameters, P, D, Q, that govern how past values and errors contribute to forecasts, but you also specify seasonal parameters, P, D, Q, and the season length M, for example, 12 for monthly data, to explicitly model those cyclical swings. On the slide's code example, the workflow begins by pulling historical closing prices for a given stock and cleaning the series to remove any gaps. The SARIMAX function is then called with both sets of orders, one for the regular ARIMA components and one for the seasonal cycle, so the model learns both the underlying trend and the repeating seasonal behavior. After fitting, the code issues a forecast command for the next 12 periods, producing a set of predictions that reflect both recent price movements and their annual rhythm. This end-to-end example shows how just a few parameters can empower you to generate nuanced, seasonally aware forecasts for financial time series. Facebook Profit is a user-friendly forecasting tool that automatically handles key challenges like seasonality, holidays, and missing data, making it ideal for financial time series with complex patterns. On the slide, the example begins by downloading historical closing prices and reshaping them into the format Profit expects, one column for dates and one for values. The model is then initialized and fitted to that data, during which it learns both the underlying trend and any recurring seasonal cycles. After fitting, Profit generates a future calendar of dates and predicts the corresponding values, producing not just point estimates but also confidence intervals. Finally, it plots the historical points alongside the fitted curve and its forecast, giving you an intuitive visual of past behavior and projected trends. This slide shows how an LSTM network, short for long short-term memory, can learn patterns over extended sequences to forecast the next point in a financial time series. On the left, the code first pulls historical closing prices, then chops that series into overlapping 10-day windows paired with the immediately following value. Those windows are reshaped into the three-dimensional format LSTMs require: samples, time steps, features. The model itself is a simple sequence: one LSTM layer with a set number of hidden units to capture temporal dependencies, followed by a single output neuron that makes the next day price prediction. During training, you see the loss printed for each of 50 epochs. This loss curve tells you whether the network is fitting the data better over time. Finally, the code uses the most recent 10-day block to produce a concrete forecast, here around 255, showing how the model turns learned sequence patterns into real numerical estimates. This end-to-end example illustrates how just a few building blocks, a data loader, a windowing routine, an LSTM layer, and a training loop, can combine to create a powerful forecasting tool. Exponential smoothing, or ETS, offers a powerful yet intuitive way to forecast time series by explicitly modeling three components: error, trend, and seasonality, without requiring deep neural networks. In the example on the left, the code first ensures your data has a proper date-time index and consistent business day frequency, then forward fills any gaps so the model can train uninterrupted. The exponential smoothing function is configured with additive trend and seasonal terms, and a seasonal period that matches the data's cycle. Here shown as 5 units, but you'd adjust that for daily, monthly, or yearly seasonality. Behind the scenes, the model uses weighted averages of past observations and errors, with more recent values carrying greater weight to learn both the underlying direction and repeating patterns. After fitting, it generates a 12-step forecast, which the plot on the right overlays as a red dashed line against the blue historical series. Seeing the forecasted curve smoothly extend the real data shows how ETS captures both gradual trend shifts and cyclical swings, giving you reliable, statistically grounded projections for your financial time series. Gaussian processes offer a fully probabilistic approach to time series forecasting, learning both the shape of complex nonlinear trends and the uncertainty around them. In the code example, we first reshape our historical price series into a simple one-dimensional input, time steps, and output, prices format. A composite kernel, combining a constant term and an RBF kernel with wide bounds, lets the model flexibly fit both broad levels and local variations without getting stuck during optimization. By initializing the Gaussian process regressor with multiple optimizer restarts and Y-value normalization, we give the model the best chance to find robust hyperparameters. Once fitted, it predicts mean values and standard deviations for the next 12 business days, which we align to actual calendar dates in a pandas series. The resulting plot overlays our blue historical curve with a dashed orange forecast and shades the confidence band in gray, clearly showing both the predicted trajectory and how our uncertainty grows as we look further ahead. This approach not only captures irregular market patterns, but also quantifies how much trust we can place in each future estimate. When working with financial time series, the first step is always to visualize your data. Plotting price histories, rolling averages, and seasonal cycles helps you spot underlying trends or repeating patterns before you even touch a model. For classical methods like ARIMA or SARIMA, you must ensure your series is stationary, using differencing or detrending to remove persistent shifts. When you move into machine learning or neural networks, normalizing or scaling your inputs makes a huge difference in training stability and convergence. Always reserve a portion of your data for validation. Testing your forecasts on unseen points prevents overfitting and tells you which approach generalizes best. And remember that markets change, so retraining or updating your models regularly with the newest data will keep your predictions sharp. All of the code examples we've discussed in this lecture are available as downloadable Jupyter notebooks, so you can review each step in detail and run them yourself. This brings us to the end of our time series module, where we've covered a range of powerful forecasting tools, from the classical ARIMA and SARIMA models that capture statistical patterns and seasonality, to Facebook's profit for handling holidays and irregular events. We've seen how exponential smoothing, ETS, explicitly models error, trend, and seasonal components, and how LSTM networks learn long-range dependencies and complex nonlinear data. Gaussian processes then add a fully probabilistic layer, giving us not only predictions but also a clear measure of uncertainty. By combining these techniques, you'll be able to choose the right approach for any forecasting challenge, whether you're analyzing stock prices, economic indicators, or business KPIs, and deliver more accurate, trustworthy insights across finance, economics, and beyond.